Hello everyone, thank you for watching another video lecture about database. In this lecture, we are going to study relational databases. Relational databases are fundamental aspect of modern data management, organizing information in structured tables or relations with attributes. These attributes define data properties. The schema represents the database design, by instances refer to the actual stored data. Based on mathematical principles like set theory and relational algebra, relational databases uses keys like primary keys, foreign keys, candidate keys in order to ensure uniqueness and maintain relationships between tables. Relational query languages such as SQL enable efficient data manipulation and retrieval, utilizing operators like selection, projection, joining, etc. Understanding these concepts is essential for designing and managing efficient database systems. Let's get started. We start with the foundation of this presentation, the relational model, or RM in short. This is a method for organizing and managing data in a structured way. How? Using tables. It was pioneered by Edgar F. Cote in 1969, and its core idea is simple yet powerful. All data are stored as tuples. Think of these as rows in a table, and these tuples are grouped into some relations, which are tables themselves. This approach provides a systematic way to store, retrieve, and manipulate data, forming the basis of modern database systems like SQL. We introduce two key terms here. One is relations and attributes. Relation is necessarily a table that holds data, and attributes, as you can see here, like ID, name, salary, department name, these are the columns of our table. Each column represents a specific type of information. Like, for example, ID here, names here, departments here, and salary here. Tables are building blocks of our database. So we call these things are tuples or rows or even records. Once again, relational models represent how data is stored in relational databases. A relational database stores data in the form of relations, or you can say tables. It means relational databases represent the database as a collection of relations. Now let's dive into the properties of attributes. Each attribute has a domain, and the domain is the set of permissible or possible values that an attribute can take, like numbers, strings, etc. Attributes should be atomic. It means they are indivisible. You won't split a telephone number into smaller parts within a single column, or even names or family names. Finally, we have null values. These null values represent missing or unknown data. In other words, a null value is neither an empty string for character or the date-time data types, or it's not zero for numerical data or types. Here we can see an example of relation. The table has four attributes: ID, name, department name, and salary. Each attribute has a domain. This is the domain for ID. Possible numbers that we can assign to ID. Possible name or possible department that we have here, or salary that we have here. This name can get only these values. Department name can get values including possible department in a university, for example. Let's formalize things. Attributes are denoted as A1, A2, up to AN, representing the columns of a table. Then we have relation schema. This is a blueprint of a relation. We write it as R A1, A2 up to AN, listing all its attributes. For example, the instructor relation has attributes like ID, name, department name, and salary. This schema defines the structure of table before we even add data. It's like the architectural plan for our database. Here is where we can connect the schema to actual data. So a relation is a set of n tuples where each tuple is a row or record, and each value AI, A1, A2, A3 belongs to the domain of the attribute that we have. The relation instance, this is the snapshot of data in a table at a given time. You can say its current value. Each tuple is a row or record, like a record for one instructor in a table. We also define two metrics here, degree and cardinality. Degree is the number of columns in a relation, and cardinality is the number of rows or tuples in a relation. These terms help us describe the size and shape of our data. Here we can see an example, the instructor relation. Notice that the order of row doesn't matter. Which one is first after doesn't matter. Whether Einstein is the first or another one is the first, it doesn't matter. The table has four attributes: ID, name, department name, and salary. And we have here like 12 records. So four attributes, 12 records. Each row is a tuple, right? This is, we call it as a tuple, row, or record. This unordered nature simplifies storage and retrieval, focusing on the data itself rather than its sequence. Why do we use relational model? It's simple. Data in tables is intuitive. It offers structure independence, meaning the structure can change without affecting applications. It's easy to use for users and developers alike, with strong query capabilities through language like SQL. It provides data independence, separating logical design from physical storage, and it is scalable, handling large data sets efficiently. These benefits make it cornerstone of database system. No system is perfect, and the relational model has drawbacks. Complexity arises when managing large interconnected databases. Relationship and queries can get tricky. Isolated databases mean that data might not integrate easily across different systems, leading to silos. While these are challenges, they are often mitigated with good design and tools, but it's worth noting these limitations. Let's get mathematical. A relation can be represented as a triple: TL, T name, H, and E. T name is the name of our table, H is attributes A1, A2, A3 up to AN, and E is records. Like for example, here we say 2222 Einstein physics number. This is one record. This formal notation ties back to our example table, showing how the relational model is both practical and theoretically grounded. In databases, keys which ensure data uniqueness are very important. First, we have a super key. It's a set of attributes that uniquely identifies each tuple, like for example ID or name for the instructor table. Then we have candidate key. This candidate key is a minimal super key, meaning no subset of it can still uniquely identify tuples. So here we have ID. It's a candidate key because it's enough on its own, while ID name includes an unnecessary extra attribute like name is not required because ID is exclusive. Building on keys, the primary key is the chosen candidate key to uniquely identify tuples, like ID in case of instructors or username in case of emails. Then we have foreign key. A foreign key links tables. It's a primary key from one relation, like department name in table department, that appears in another one, like for example in instructor table. So we call referencing relation and reference relations. The referencing relation that in our example instructor use reference relation department to connect data, ensuring consistency across table. So when we want to connect instructor table and department table, in this case, our instructor table is referencing relation and our department table is reference relation. In here, we can see a schema diagram for a university database. How many tables we have? Text table, student table, advisor, department, instructor, and many tables. For example, a student table has ID, name, department name, and total credit. This ID is the primary key here, right? Then we have added to the department. Department is here primary key here, but in here it is a foreign key because it's connecting two tables together. Now we explore how to query data. Relational query language come in two flavors, procedural and non-procedural. In procedural, it means step-by-step instructions, and non-procedural or declarative specify what you want, not how. Then we have three pure languages. These are relational algebra, operations on relation. Then we have tuple relational calculus, tuple-based logic. And we have domain relational calculus, which is domain-based logic. These form the theoretical basis for practical language like SQL. In relational databases, we work with several operators including selection, projection, union, difference, joining, Cartesian product, renaming, etc. The first one is selection operator. This is used to filter rows based on a condition. So we have a relation R here, A, B, C, D. Now we want to do the selection. Selection, it says A is equal to B and D greater than 5. It means A and B should be equal and this is AND operator, right? So this one, A and B are same, equal, and D is also greater than 7. So this will come to here. This one, A and B are not equal. So we do not. This one, A and B are equal, but D is not greater than 7. So not here. This one, beta and beta same, and 10 is greater than 5. So this one will come to here. It's a kind of filtering. Then we have projection operator. This is selection of columns, right? So the project operation select specific columns. For example, we have relation R and we want to select, so in here we have A, B, and C. Out of these three columns, we want to get only A and C. We show by pi. In here, we show the selection by sigma. In here, we show by pi. So A and C, it means we don't need B. So A and C will be here. And also because we have here repeated, so we will consider this one only 1, 1, and 1, right? This is how projection works. Then we have union of two relations. This union operation combines tuples from two relations. For example, here we have R and S, right? So R and S, when we say union, it means all of them, or you can say OR operator, right? So alpha and 1 will come here. Alpha and 2, because both same, it's common, so it will come once only. Beta and 1, beta and 3, all together, or you can say union. It's a way to merge data from compatible relations, ensuring no repetition. Then we have set difference. This set difference find tuples in R that are not in S, and we show by minus. So we say R minus S, so whatever is in R but not in S. So alpha 1 is here but not here, so it will come to the result. Alpha 2 is here, it's here, so it will not come to here. Beta 1 is here, not in here. We'll come to here. How about beta 3? Beta 3 is in S, not in R. So it will not come to the R minus S. The intersection operation finds tuples common to R and S. So this is uh, similar to AND, or you can say intersection, right? So it means the record must be in both of them, right? So alpha 1 is not in here, so it will not come here. Alpha 2 is in both of them, so it will come to here. Beta 1 is in here, but not in here, so these two will not come to here. Intersection highlights shared data, defining our focus to what overlaps between relations. Then we have Cartesian product. This Cartesian product combines every tuple in R with every tuple in S, creating a large table. What it means, we show by this multiplication sign or times. So for every record in R, all the recorder in S will be repeated. So we have alpha here, and in here, alpha 1, and all the relations of the second one are repeated only for alpha 1. Then we have beta 2, so beta 2 is here. Records of S table are repeated here. So in here, for Cartesian product, sometimes we want to do R and S, and we have a same column, B here, right? In this case, we write R dot B for this one, and for this one, we write S dot B. Alpha 1 and all together. So alpha R dot B, so alpha 1 is here, all are here. Then for this one, all of this one, you can see this is Cartesian product. The rename operation we show by row xe assign a new name x to a relation E, right? We have a relation R here and we want to rename it, right? So we say R multiply Cartesian product of a copy of it, but with the new name S. So you can see here RARB, this is the previous one. Just we make a copy of R and we name it as S. So SA and SB. Then we did Cartesian product. For each row of the table, all the row of itself are again here, right? So just we copy paste R and we rename it as S. This is useful in queries to avoid confusion when using the same relation multiple times. We can combine operators. So for example, here we say Cartesian product of R and S, then out of that one, we want to select the records where A is equal to C. So it means we will do first a Cartesian product of R and S, then out of this one, whenever A and C is same, we will take out. So this one, then this one, then this one will come to here. And because this is repeated, so it's one time only, this is one time and this is one time. The natural join we show like this bow tie, something like this. This operation we show the natural join merge R and S based on common attributes. For each pair of tuples, if they match on these shared columns, combine them into a new tuple. Unlike Cartesian product, it only keeps matching pairs, reducing redundancy. This is a key operation for linking related data across tables. So here is natural join in action. R and S, so we have A, B, C, D, and we have B, D, E here. So these two are the same, right? These B and D are the same. Then we say R bow tie S or natural join S, right? In here, this operator matches tuples where B and D are equal. For this natural join, first we do the Cartesian product, then whenever RB and SB are the same and also RD and SD are the same, we will take out selection. Then from the result, we will select A, RB, C, RD, and E only one of them, we avoid repeating. So after doing the Cartesian product, we take out whenever RB and SB are the same. So this is RB and this is SB. This is D and D same. So it will come here. Alpha 1, alpha A, and alpha. So these records came here. Then it was Cartesian product, right? Alpha 1, alpha A, and gamma, right? Etc. We can go. So this is the expansion part of the natural join. First, you do Cartesian product. Then out of the Cartesian product, we will select the records where r dot b is equal to s dot b and r dot d is equal to sd. Then we will take out the columns of a, r dot b, c, r dot d, and e. So in Excel, you can do the natural join like this. First of all, you do Cartesian product. So this is our R and this is our S, right? So first of all, we do Cartesian product. So out of the Cartesian product result, it will be something like this. So for example, A, this is one table, one for the first row. You can see we have repeated all our table, SB, SD, and E. You can see here. For the second one, we do the same. For the Y, we do the same for A and for C. Then, whenever B2, it means this one is equal to E2, this one we take out. And also, whenever this one is equal to this one. Then, out of this one, we selected A column, R dot B, C, R dot D, and E. This is how natural join works. Once again, I will do Cartesian product, then I will select the records when r dot b is equal to s dot b and r dot d is equal to s dot d. Then I will select columns, A columns, R dot B columns, C column, R dot D columns, and E. You can practice this one in Excel to better understand how it works. Back to query language, a query takes table as input and also the output is a table. Beyond algebra, we have aggregate operations like sum that total values, average of them, max, the highest value, and mean, the lowest value. These extend relational capabilities, letting us analyze data like calculating average salaries in the instructor table. So here is a summary of what we studied so far. We had selection operator, the symbol was sigma, and for example, I want to take out the records in the instructor's table where the salary is more than $85,000. Then we had projection operator, we show by pi, and in here we select columns. It means in instructor tables, I'm interested in ID column and salary. Then we have Cartesian product, we show by times like Cartesian of two tables. Then we have union, it means, for example, you do projection of two columns in two tables, name and student, name in instructor and name in student. Then we have set different, we show by minus, and in here we are interested in columns that are available in the first one but not in the second one. And in natural join, we show by bow tie, and in here we do the Cartesian product, we select the rows where the common attributes are equal, we select the unique interested columns. To conclude, the relational model introduced by Edgar Coe revolutionized data management with its structured table-based approach. Through this presentation, we have explored the relational model concepts like relations, attributes, schemas, and instances, and we have seen how keys like primary key and foreign key maintain integrity. We have also delved into relational algebra with operations like selection, projection, natural join, showing how to manipulate and query data effectively. The model's advantages like simplicity, scalability, and query power make it a bedrock of modern databases, despite challenges like complexity. This foundation equips us to design and interact with database efficiently as a skill as relevant today as it was in 1969. Thank you so much for your attention. Please feel free to ask me if you have any questions by leaving a comment below this video, and see you in the next lecture.